Alright, another video to go today. We have a few concepts to get through, so I'll spare you the details of going through all of them. You can see them there. But let's get cracking. So, firstly, we've been over this before in our videos on motion, but we have two different types of motion. Linear motion that occurs on either a straight line, which we call rectilinear, or on a curved path, which is called curvilinear. Okay, and then you have angular motion, which is just rotational motion. Now, there's a lot of words which are very similar to the linear words, and they've just added angular, and they can confuse a lot of people. For example, inertia and moment of inertia, velocity, angular velocity, displacement, angular displacement. All it is the exact same thing. It's just talking about rotational movement. So you can see a high jumper on a high bar there, forming a rotation. So anything where we're talking about a rotational movement, we're talking about angular motion. So therefore, the terminology changes, but the principles are still exactly the same. So I'm hoping I can prove that to you throughout this today. So there's again some of the key words that we're going to go through. Newton's 3 laws is on another video, so I won't be going through that one today, but all the others we will. So mass is pretty straightforward. A person with a larger mass is composed of larger quantities of matter. And there's a direct relationship between the amount of mass and an object's inertia. So let's get into inertia. So it's a measurement of how difficult it is to change the motion of an object. Okay, so if it's motionless, if it's stationary, then an object with a large amount of inertia wants to stay stationary. So it's going to take a larger amount of force in order to overcome that inertia. Okay, an object with a little bit of inertia is only going to take a little bit more force than that inertia in order to make that object move. But this occurs also in moving objects. They also have inertia. So an object that is moving with more inertia is harder to stop. It's got more momentum. So it's harder to stop. It's going to take a great deal of force in order to stop it. More force than the inertia anyway. So it's directly proportional. So whenever you see that, it just means there's a linear relationship. As mass increases, inertia increases. That's all directly proportional means. As one increases, the other one increases by the same amount. They're directly related in a positive way. Okay, so, and I've already just been to, but a body at rest is reluctant to move. Okay, we call that static inertia. Okay, so a sumo wrestler not being pushed with enough force in order to move it is demonstrating inertia. Okay, and a rugby player can demonstrate dynamic inertia. They're charging at the opposition fullback, and they don't want to be stopped. And it's going to take a lot of force in order to overcome their inertia and cause them to change their momentum. Okay, here's a quick little question about that. Which of the following weights would have the greatest amount of inertia? So, hopefully, we were able to identify that A, the heaviest the object will have the most inertia. Direct relationship, remember. Okay, force, it can change the shape of an object, it can stretch it, it can squash it, it can twist it, it can move the object from the starting position, it can accelerate it, it can slow it down, decelerate it, it can change the direction that it is moving, it can cause it to move when it's stationary, and it can cause it to stop when it is moving. Okay, so all of those things are what force can do, and we measure this, and you'll be familiar with this with Newton's second law, the law of acceleration. With force equals mass times acceleration. So the more mass something has, it will travel faster than something that is lighter with the same amount of acceleration. Likewise, if you have two masses that are exactly the same, the one with more acceleration will have more force. Okay, so those two things combined can give us the total force that an object has, and the force is measured in newtons. Okay, forces need to be sufficient enough to overcome the body's inertia, as I've explained already. Okay, so there's the example there. A heavy barbell on the floor is at rest. It's not moving. Okay, it has zero velocity, zero acceleration. In order to change that, the weightlifter needs to use more force than the inertia of that object in order to overcome that desire for this object to stay at rest. All right, so it needs to require more force than the inertia force of the barbell itself. Okay, so again, you can pause that and have a read of some further examples. Friction. Friction is one that should be pretty easy to understand, but we'll go through it and see what you think. It's a force that opposes the motion. So what that means is whichever way the motion is traveling, then friction is working in the opposite direction. So if it's working against motion, it's inhibiting or slowing down the motion or decreasing the amount of motion. Okay, so it works in the opposite direction. That's what we mean by when we say it opposes the motion. Okay, rough surfaces will have more friction. All right, if you think about it, something that I'll show you on the next slide, but if you think about something that's rough versus something that's smooth, which one can slide more easily, it will be the smooth object. Okay, so smooth objects have less friction, which means they move across their surfaces with more fluently, less inhibited. Okay, there's some other things which can change the friction between two surfaces. Water, ice, and oil will also decrease friction, whereas chalk and grippo will increase friction. Grippo is used in AFL to add more grip on their hands, and I believe NFL use it also. Okay, so here you can see this person, a very stick figure, not the best drawing in the world, but you can see very clearly they're walking to the left of screen, and as their foot comes in contact with the surface, friction is working the other way. Okay, so that allows them to grip, okay, because it's working in the opposite direction of the motion, and that helps them to grip on the surface that they're between the two surfaces. Because remember, it's a surface friction. There has to be two surfaces interacting for friction to be present. Okay, so you can see why that happens just by looking at surfaces. So you might not think a rough surface looks like that, but if you look at it in a high-powered microscope, you will see that it is quite rough. Even something like carpet is very rough, although it appears smooth to our naked eye. So, yeah, you can see the smoother the object, the less friction. So the more easily the motion will occur between those two surfaces. So, why do they do this in sport? Why would you want to decrease friction? Well, downhill skiing, you want flat, smooth skis that allow the performer to move faster over the snow. Okay, so they want to go as fast as they can in downhill skiing. So decreasing the friction helps them to do that. Wheels on rollerblades aim again to decrease the friction, and therefore they can increase their speed on the rollerblades. Okay, contact sports like AFL, they oil up their arms to decrease the friction, and it makes it more difficult for their opponents to hold onto them in a tackle. So they can't be gripped as easily. Their hands slip off because there is less friction. So it's harder for them to get a hold of them. Why would you increase friction in sport? A weightlifter, a gymnast, rock climbers, they all use chalk to increase grip between their hands and the barbell or the rock in which they're trying to either lift or hold. Stops on football boots, again, make it a rougher surface so they increase the friction, which in turn increases that athlete's stability and ability to grip the playing surface. Surf wax on a surfboard also increases friction, and gloves in golf increase the friction between the hand and the club. So you can see very clearly the smoother very easily it's going to glide over that surface, where if it's rough, it's going to really claw into that surface and really slow it down. So different depending on what the purpose is and what the objective is, then it depends on whether you want to increase it or decrease it. Just another couple of examples. Just look at the tire difference between a road bike or a race bike on the left and a mountain bike on the right. Say a mountain bike, they're going to obviously be going downhill on dusty, not even paved roads. Okay, so they need a lot of grip and a lot of friction in those difficult surfaces. So whereas on a road bike, they don't. They want to go as fast as they can on an asphalt surface, so they don't need to grip the road as much. In fact, they need to glide over it. So they want to decrease the friction, a road bike, whereas a mountain bike wants to increase the friction. Okay, you can see the surface on tennis courts. As you know, there's multiple different tennis court surfaces. Here we have the clay court, famous French Open. Okay, and as many other events, but you can see the just how loose the rock is on top of the surface. So that means there is not much friction at all. Okay, so it's a less friction between the player's shoe and this clay surface. It's important that you talk about the two things that are interacted. So it's not Rafael Nadal and the surface, it's the shoe of Rafael Nadal, or the sole of the shoe and the clay surface, to be more exact. Okay, player finds it harder to grip on this surface, and change direction quickly would also be very difficult. But due to the loose gravel, there's going to be less friction, and that will allow them to slide in and reach the ball, which they wouldn't be able to do on another court, which we'll see right now. Okay, so same tennis player, different court, so they would need to alter not only their technique but their equipment in terms of their shoes in order to suit this surface. Okay, but there is increased friction on a hard court surface compared to the clay court, and there's no it doesn't take a rocket science to work out why. There's loose gravel on top, so there's going to be not much grip. It's going to be a rougher surface, but the surface is not stable. The rock move on top, so it's actually going to be less friction between those surfaces. Okay, whereas this one, it might appear to be smoother, but it's fixed. Okay, it's not going to move with his foot as it goes across. It's going to stay right where it is. So that means there is an increased friction. Okay, and because there is an increased friction, the foot will grip, and he'll be able to turn a bit more with a bit more agility when compared to that on a clay court. So, but the downside of that is they'll be unable to slide to reach a ball on this surface. Okay, because they're just not going to be able to slide across that much because there's too much friction between their foot and the surface. Okay, there's a few more friction videos there, but hopefully that now makes sense. So gravity, I'm not going to spend much time on this because I think it's pretty straightforward. Any object on Earth is subject to gravity. Okay, Earth being such a large figure, when we jump, the reason we come back down is because we're being pulled to the center of the Earth. Okay, so gravity affects anything that is in the Earth's atmosphere. All right, and we can work out the gravity. Well, we know the gravity on Earth is 9.8 meters squared. So using that and someone's mass, we can work out what the weight force is of a person. Okay, but here we have two diagrams. The one down the bottom here of the ball falling the ground shows what happens here on Earth. Okay, the point of release, the angle, the speed of release, everything is exactly the same. Okay, but this bottom one had gravity affecting on the ball. So gravity eventually brought that ball back down to the surface in what we call a parabolic path. Okay, so that curved motion that all projectiles go in, okay, we call that a parabolic path. Okay, and the other tennis ball shows what would happen if there was no gravity. This ball would just continue on the same straight trajectory that it was thrown. Okay, so as you can see, gravitational force will affect all objects in the Earth's atmosphere to its gravity of 9.8 meters a second squared. Okay, so you can go to this website and calculate what your weight would be on different planets, because each planet has different gravitational fields, which means the amount of gravity you're experiencing will be different, and therefore your weight will be different. So have a look at that. Right, now we're looking at drag force. So when it comes to drag, an object moves through water or air, it experiences a drag force. So it's not wind. It's very different to wind. Doesn't matter if you're going with the wind or against the wind, air resistance is still working against you. Basically, as you move, there are air particles in your way, and they are opposing your movement. Okay? So whichever way you're heading, then air resistance is working the opposite direction. So you can see here, this person is heading to the left of screen. Air resistance would then be working against them to the right of screen. All right. And air resistance hits every part of your body that is moving in that direction. So it'll go normally over his head. He obviously won't feel any air resistance that's not touching him. It's only the ones that are touching him that he is going to feel. So if all other forces are equal, an increased drag will mean a slower speed of the rider. Okay, a decreased amount of drag will result in an increased speed. So basically, when we're talking about the drag, we're talking about the air resistance. So if there is more air resistance, then you're going to go slower. If there is a less air resistance, then you will be able to go faster. So there are ways that athletes can manipulate this in sport. Okay, its drag or air resistance is affected by the shape of an object in motion, otherwise known as the cross-sectional area. I'm going to go into that in a second. The speed that the object is moving at, and whether the surface is smooth or not. And also the air density, the thicker the air that it's trying to move through, and that might be based on altitude, then the harder, the more drag force there's going to be against that person when they're in a high level of air density. So this is the same in water as well. It's not just in air. Okay, so and here you can see very clearly the effects of your shape. All right, because remember, this person is moving from left to right. So they're moving from left to right. The water flow or the drag is going from right to left. And you can see in this top picture, they've made themselves nice and skinny. So the cross-sectional area is literally just the vertical area in which the water can touch on when it's going from right to left. Okay, so you can see in this streamlined person, they're having much less disruption from the drag. Okay, when you compare it to the second person, they've got their head up, their chest is out a little bit because their head is up, their feet are down a little bit lower. And what this is meaning is there's more drag. There is more water hitting this person at any one time. And because there's more water hitting this person, they're experiencing more drag. It's going to slow them down more because they have more force that is working against them. They have to work harder in order to get the same speed, or they're just going to go slower, which is the more likely of the two. So you can see an example of that here. This also goes on to our next point, which is speed. The person in the top part of the photo is doing freestyle. The second part is doing breaststroke. So freestyle can go much faster than a breaststroke swimmer because of the style of stroke and the sort of the pace that the stroke goes at. And what the relationship is between drag and speed, the faster you go, the more drag you experience. And you can see this here by the ripples of the water. There is more drag from this top person than there is on this bottom one, and that has got to do with the speed at which they are traveling. They're both fairly streamlined. You could probably argue that this person is a little bit less streamlined because their hand and their head are a bit further apart, whereas this person's fingertips and face and whole body is in one line, and that's what they mean by streamlined. Okay, that you're keeping yourself in a very thin line so that your cross-sectional area is small, and because your cross-sectional area is small, you're experiencing less drag. Okay, there's less particles pushing against you when you're trying to move the opposite direction. Therefore, you're not slowed down as much. Okay, so you can see the shape, or every point of the person that is opposing the direction of motion. Okay, they're going to the right of screen. Each one of those red arrows represents an area of them which is going to experience the air resistance. So if they're standing up really tall like that, it's clearly going to make them experience more air resistance or more drag, and therefore they're going to slow down a little bit more. So how can you change that with technique? Okay, if someone squats down, let's say for argument's sake that these two are the same person, okay, the only thing that they've changed is their shape, this person would experience probably half the amount of air resistance as this one because their shape is half the size. So there's going to be half as many particles hitting them as they're trying to move, and therefore half as amount of force slowing it down. Okay, another example of this is a peloton. In cycling, you'll notice when there's a huge pack, and quite often people go out and try and race in front of the pack, and more often than not, the pack of all these people manages to catch up to the person who's out there by himself. And it's a really interesting thing about why this happens. Well, if one person's out by themselves, they're experiencing 100% of the air resistance. Okay, so the drag is hitting them front on. There's no protection from that drag or air resistance against them. Okay, so that person who's miles ahead of the peloton has to work harder because they have 100% of air resistance hitting them. You can see what happens here as people move down the pack. Even this person here, who's only behind 3 people and in line with 2 others, okay, they're experiencing 35% of the air resistance as this person is at the front because they have that protection. They're not hitting as many particles because the people in front of them are hitting those particles. And this only gets less and less when right down till we get this person right at the back, who's only experiencing 4% of the drag as compared to this person at the front. So what happens in a peloton is these people will rotate through position. So this person might be at the front for 5 minutes, then it might be someone else's turn, and this keeps everyone, makes everyone spend a lot less energy. And because they're spending less energy, they're able to go a bit faster, and they eventually, so sometimes, most of the time, catch the person who's out in front of the peloton. Okay, so as I said before regarding the speed, the faster someone is going, the more drag force they're experiencing. You can see the person's cheeks who's doing the skydiving there, they're flapping around. If someone was running on the earth, that would not be happening because they're not reaching speeds fast enough for air resistance to have that effect. Okay, so if we're looking at 2 cyclists, they weigh exactly the same, and they have the same shape, everything else is the same, and one's going at 30 kilometers an hour and the other one's going at 20, the one at 30 will experience more drag against them. Okay, so yes, they are going faster, but they're having to work harder in order to stay 10 kilometers per hour faster than the other cyclists because of the increased drag that they are facing when compared to that person who's going slower. Okay, an increase in speed results in an increase in drag. All right, remember, drag's working against it. So when you're in a race and it's a time-based thing, You do not want drag. You want to minimize drag. Okay, but basically the faster an object, the more drag force is against it. Okay, how can we intentionally decrease drag? So Michael Klim here shaves his eyebrows and shaves his head. Why? To make it a smoother surface. Because if there's a smoother surface, and there's less little pockets that the drag can get stuck and therefore cause a higher pressure and slow him down even more. Okay. Same, we've got Stephanie Rice here, an Australian Olympic gold medalist, multiple. If she swam with her hair out, like in this photo on the left, okay, she would have a much rougher surface as she's swimming in the water, as opposed to this smoother surface. So this swimming cap allows her to decrease the amount of drag and allows her then to swim faster when applying the same amount of force. Okay, and you can see what happens when the shape of an object is not streamlined. This streamlined shape allows the air down the bottom to come over it and just slip off the back of it. Okay, it doesn't create this low pressure zone and turbulence behind it and a high pressure zone in front of it, which slows down. It increases the drag on this top object. This bottom object, yes, it's still going to experience drag, but nowhere near as much because this shape allows that drag to slip off the back of it. Okay, and you can see the design of these bobsleds support this shape. Okay, they want the air resistance to sort of glide off it rather than hit a flat surface front on. Okay, where it's going to get trapped and cause the drag to increase. Okay, so by having a streamlined shape, it allows them to decrease. So that's how we can change equipment to be more streamlined and therefore experience less drag. You can also notice they've done some technique here to decrease their drag. The back three people, other than the driver who's just poking the top of his head out, the back three have all ducked their heads down, and that would be to decrease the size of their shape and therefore decrease the cross-sectional area which is exposed to the drag. So that's going to allow them to move faster because they experience less drag. Okay, and you can see these helmets, another piece of equipment in order to decrease drag. When a racing cyclist, they wear this top hat, they wouldn't wear this motorbike helmet down the bottom simply because if they're moving from right to left, they're moving in the direction of this arrow. Air resistance is always going the opposite direction, so it's going from left to right. If it was wearing this helmet down the bottom, there's just so much room that is going to be exposed to air resistance. They're going to be slowed down so much more, whereas this smaller, more unique, and also more streamlined helmet allows them to decrease the amount of drag. Okay, but also they have technique too where they keep themselves nice and low. They decrease their cross-sectional area or their shape, again, to decrease the amount of drag that they experience as they're moving. All right, so there's a few more definitions. I hope that makes sense. I'm about to explain momentum in a separate video. Hope that one made sense to you, and best of luck.